Hello everyone, and welcome to today's webinar with projectmanagement.com in conjunction with Construx, Stranger Than Fiction, Case Studies in Software Engineering Judgment. My name is Andy Jordan and I'll be the moderator for today's session. And just before I introduce our speaker, a few brief admin things for everybody. First of all, this session is being recorded, so if you can't stay for the whole session, or if you want some colleagues to listen to this, you will be receiving a link approximately 24 hours after this recording with details of how to access the recorded version. And at the same time, we'll also be including a link to the slides, so you'll be able to get access to all of the presentation material as well. This session is eligible for a PDU, and before we wrap up the webinar at the end, I'll give you details on how you can access the PDU information. And we also have some time for questions. So if you have any questions as we go through this presentation, please feel free to type those into the chat window in your GoToWebinar console, and we will try to get to as many of those as we can before we get to the top of the hour. Finally, the audio is being streamed through your computer, through your speakers, so if you're having any audio difficulties, just check your audio settings and you should be okay there. So with that said, let me introduce today's speaker, which is Steve McConnell, who I'm sure many of you already know. Steve is the CEO and Chief Software Engineer at Construx Software, where he consults to a broad range of industries and oversees Construx's consulting and training offerings. Steve is the best-selling author of the industry classic Code Complete, as well as Software Estimation, Demystifying the Black Art, Rapid Development, and other titles. Steve has served as editor-in-chief of the IEEE Software Magazine and chair of the IEEE Computer Society's Professional Activities Board. Readers of Software Development Magazine voted Steve one of the 3 most influential people in the software industry, along with Bill Gates and Linus Torvalds. Steve can be reached at stevemcc@construx.com. So without any further ado, Steve, over to you.
Thank you, Andy. Well, it's a pleasure today to be able to talk about Stranger Than Fiction, Case Studies in Software Engineering Judgment. In this case, the title is actually pretty literal, Case Studies in Software Engineering Judgment. I want to begin today by going through a discussion of judgment using something called Bloom's Taxonomy as the basis for that discussion. Then I want to introduce something called the 4 factors model that I believe can be used to support judgment in software engineering. And then I want to go through a few case studies in applying software engineering judgment. So let's turn then to the topic of judgment and introducing that, as I said, through the use of Bloom's Taxonomy. Bloom's Taxonomy is basically often used in education for the purpose of designing coursework, exams, and that kind of thing. At least that's where I first ran into it. And it basically talks about different levels of understanding, going from knowledge at the simplest level of understanding out to analysis, synthesis, and judgment at the most advanced level of understanding. What we see is that if you do a web search for Bloom's Taxonomy, you'll find lots of references to it, but mostly having to do with instruction and assessment in an education setting. And I think that in many of these descriptions of Bloom's Taxonomy, the model is really described superficially, even flippantly, almost like a punchline. But in looking at it deeper, I really believe that a deep, genuine understanding of Bloom's Taxonomy, especially the upper levels of analysis, synthesis, evaluation, has profound implications for software professionals, has profound implications for how we recruit professionals, how we develop professionals, even how we think about the work that we do ourselves as software professionals. So let's take a look at the different levels of the taxonomy and see how they apply. The lowest level in the taxonomy, knowledge, is about remembering previously learned material. It's a recall. It's really exactly what it sounds like. So in software engineering, examples of knowledge would be things like recalling something that you learned from a book, or recalling a personal experience, or remembering the details of specific technical practices, maybe recalling patterns of practices or successes or failures or that kind of thing. So obviously recall is something we do all the time. It's typically shown in the diagram of Bloom's Taxonomy as the base of the pyramid, and I believe that truly is the case, that knowledge does make up the foundation, and that we have to have a really good knowledge base to support everything else. The next level in the taxonomy is comprehension. And as it says on the slide, comprehension means grasping the meaning of material. So rather than just repeating back verbatim what we've heard, we have to show that we comprehend it. So summarizing something, like summarizing Scrum, would indicate comprehension. We're not just repeating back details exactly as we learn them, but we're summarizing them, which shows a higher level of understanding of the material. Being able to explain Scrum, either in words or as a diagram, would be another example of comprehension. Giving an example would be another example of comprehension. Explaining why Scrum is not a design approach. Now, anybody who's familiar with Scrum knows that that's a very blatant example. Scrum's not a design approach, but explaining why would indicate comprehension. Or explaining how Scrum is different from extreme programming. In Bloom's taxonomy, this is considered to be the lowest level of understanding, meaning kind of the simplest or entry level of understanding. The next level in Bloom's taxonomy is application, as we work our way up the Bloom's taxonomy pyramid. And application is about applying or using knowledge to solve problems in new and concrete situations. So examples in software engineering would include things like using our general knowledge of design to solve a specific design problem, so applying general knowledge in a specific case, or using general project planning knowledge to plan a specific project, or general construction knowledge to write a specific piece of code. So really, application is more or less what you probably would think it would be. Moving then to the first, I think, really interesting level in Bloom's taxonomy is analysis. An analysis is about breaking a problem into its parts so that its relationships and organizational structure can be understood. So analysis is fundamentally about decomposition. It's about breaking something that already exists into pieces and then trying to understand the pieces with the goal, with the thought being that if we understand the pieces, that therefore we will understand the whole. So examples in software engineering include activities like breaking a large class into two smaller classes. That would be fundamentally an analysis activity. Or breaking a class into methods and data. That decomposition act is analysis. Allocating functionality and data to methods within a class. Another example basically of breaking something up. Finding flaws in a proposed design. This is something we do all the time in software, is pick something apart. The phrase pick something apart basically refers to the activity of analysis. Finding the source of a coding error. So you can see these are really kind of the bread and butter software development activities. Now let's take a little bit longer look at analysis. We often hear analysis also referred to as critical thinking. And in software development, we actually screen for analysis skills as an entry criteria for entering the programming profession at all. We will ask programming candidates questions like identifying the correct sequence of operations in a section of code, or identifying boundary conditions, evaluating off by one errors, that kind of thing. And it's interesting, as software professionals, many of whom may have been working for 5 or 10 or 20 or 30 years, we take these skills for granted, but I think it's important to recognize that these are not common human skills. I don't know if you can remember this far back to when you first started learning how to program, but I remember when I was first starting to learn how to program and first introduced to the idea of a loop and wrapping my brain around the idea of what things had to be done first and what things had to be done second. And at the time, I found that absolutely mind-bending. It was just incredibly taxing to keep the exact sequence of steps in order and remember all the dependencies, especially inside a loop where things are changing. But of course, after doing it for a while, it becomes second nature. You don't even think about it anymore. But it's important to recognize that while that might be second nature to you as a software professional, it's not second nature to most of the human race. In fact, I believe most of the human race is not even capable of doing that at all. And so the bottom line here is that most software professionals are exceedingly good at analysis. We screen for it. The activity itself makes heavy use of the analysis skill. And so we find people in the programming profession who tend to be very, very good at analysis. Now moving to the next, I would say further that what this leads to is that analysis kind of ends up being an overdeveloped muscle for many technical staff is fine. Obviously, developing it is a good thing, but overdeveloped means that it actually is overly strong compared with the higher level skills in Bloom's taxonomy of synthesis and evaluation. And when we see overdeveloped analysis skill and underdeveloped synthesis or evaluation skills, then we can see phenomena like analysis paralysis. We can also see that it leads to excessive focus on individual details. And I'm sure we've all worked on projects with people where people can't get past looking at individual details. They can't get to the point where they make a judgment because they are excessively focused on particulars, which is characteristic of overdeveloped analysis capability and underdeveloped synthesis and evaluation capability. Now, the next level in Bloom's taxonomy is synthesis. And what this is about is not breaking things apart like analysis, but putting things together to form a new organization or whole that requires original or creative thinking. So it's not just putting something back together, it's putting pieces together in a new way or creative way that actually creates something different than you had before. So examples in software engineering could include things like combining two classes into one new class that provides a new interface at a different level of abstraction, or making local versus global trade-offs in a design to create a better overall design, assembling a team of people based on strengths and weaknesses of a particular set of individuals. And I think one thing you'll see technical staff sometimes think is that the ideal programmer, that there's a model for one ideal programmer, but from a synthesis point of view, it's not the one ideal programmer, it's the assemblage of individuals who have different strengths and weaknesses that really makes the best team. Another example would be adjusting overall project plans based on progress of a set of individual teams, so assembling a larger project out of a set of smaller projects. And synthesis in Bloom's taxonomy is one of the highest levels of understanding. Some other comments about synthesis. It's also known as creative thinking. Clearly a higher level skill, and not as many people are good at it. And I think we find that technical people who have that overdeveloped analysis muscle often discount the value of synthesis. For example, we commonly see technical staff be skeptical of upper management, which by its nature has to be more focused on synthesis or creativity than on analysis. And as an industry, I think the software industry does a much better job of recruiting and developing analysis skill than it does in recruiting and developing the synthesis or creative skill, which I think is actually a little problematic for reasons we'll talk about in a moment. Judgment is, in one version of Bloom's taxonomy, the top level of the taxonomy. It's what it sounds like. It's about evaluating the value of ideas, concepts, principles, or solution methods for a given purpose. It's basically a higher order level of understanding, one of the highest levels of understanding. Now, Bloom's taxonomy was originally created in 1956. At the time it was originally created, the taxonomy had evaluation at the top of the taxonomy or the pyramid with synthesis number 2. In 2001, Bloom's taxonomy was revised to put create at the top and evaluation as number 2, and also changed the terms from nouns to verbs. I think what's really going on here with Bloom's taxonomy is that essentially the lower levels of the taxonomy truly are the foundational elements, but at the top levels, and I've shown here create and evaluate as the two top levels, actually interplay with each other and depend on each other. So it's not that really there is one thing at the top, it's that both those things at the top depend on everything below, but also depend to some degree on each other. So some examples of judgment in software engineering. These are interesting. Choosing the better of two technology paths would be one example of judgment. Choosing the best of 3 design approaches would be another example of judgment. Trying to justify a re-architecture project and make a judgment about why there's a business case for doing that would be an example of judgment. Choosing which proposed projects best support a business's objectives, so figuring out which of several projects you're actually going to do. Assessing the degree to which a new methodology will benefit an organization or harm it would be another example of judgment. Predicting the likelihood of success of a project plan. We'll get to that in much more detail when we get to the case studies in engineering judgment. Or conducting root cause analysis on a failed project, judging which are the factors that really matter. And one of the things that's really interesting about judgment is that in software we tend to find a lot of confusion between analysis and judgment. And in fact, people will apply analysis, which is that overly developed muscle, and they'll think they're doing judgment, but really they're actually doing analysis. And basically, if we think about it diagrammatically, analysis is the ability to go very far down one path in a decision tree, along multiple paths going down to a very low level. But the difference between analysis and judgment is, and so when we get to the lower levels of the tree, we tend to find the analysis results in making very fine discriminations at the very bottom of the tree. And I don't know how well you can see that in the presentation here, but the idea is intended to show very fine differences in the lower levels or lower branches of the tree. When we get out to judgment, though, the difference is that judgment is not about going deep in the tree. It's about the ability to choose the right path in the first place. And so if we're at the top of the tree and we just chose the wrong path, from a judgment point of view, it doesn't really matter how deep we went in the tree because we chose the wrong path at the very top of the tree. And so in this example that I'm trying to illustrate graphically here, any of the options on the right are better than any of the options on the left because of the very first decision. And technical staff who tend to have that overdeveloped analysis muscle will often think that if we can do further analysis at the bottom of the tree on the left side, that somehow we'll figure out that the left side is better than the right side, when that's just not the case, because from a judgment point of view, that very first decision is the main one that matters and actually drowns out every other consideration. So I think what I've seen over my career is that this is not a natural thing for technical staff. Technical staff often struggle with the idea that in some cases further analysis doesn't matter. That is, that it's safe to ignore details, and furthermore, not only is it safe to ignore details, there's no further value in understanding greater details because the judgment at the top level says we're going to go right, we're not going to go left, and further analysis of going left actually isn't going to make any difference. Now, one of the interesting things about technical staff, because of this overdeveloped analysis muscle, is that analysis in software is often mistaken for judgment. So we see examples like criticizing each of two technology paths. That could be seen as judgment, but it's not. It's analysis. Finding faults in three design approaches. It's another thing that would be an imposter. When we're asked to do judgment and find the best of three design approaches, criticizing each of the three is not judgment. It's just analysis. Identifying limitations of a current system to justify a re-architecture project. Another example of analysis masquerading as judgment, potentially. Advocacy for projects doesn't get past advocacy of one favored project. So, another example. Assessment of a new methodology amounts to religious advocacy for one methodology. I certainly have seen that phenomenon countless times over the course of my career. Assessment of project plans focuses on minutia. So that whole idea of focusing on the individual trees and not being able to see the forest. Or root cause analysis on a failed project consists of rehashing unpopular decisions. So I hope some of these sound familiar to you, but these are all examples of analysis where maybe more appropriately we would actually be looking at judgment. I believe from what I've seen that judgment capability is even rarer than synthesis in software, and it's probably rarer overall, not just in software. And I would say that in the software field, we hardly screen for judgment in software staff at all. For example, Microsoft's famous interview questions are nearly all about synthesis. And that's actually better in terms of Bloom's taxonomy, or it's at a higher level than we find in typical interview questions, which often are more about analysis. We find business staff complaining about poor business judgment among technical staff. They do that so often that actually is kind of a cliche in our industry. And so the $64 question really becomes, if we're not recruiting for judgment, and if technical staff is really heavily biased toward analysis in the first place, then how do we go about developing good judgment in software professionals? And that's really what I'd like to turn to next. I have a model for, I think, that supports developing good judgment, which is something I call the 4 factors life cycle model. I'm developing a lecture series which will be made available shortly. I'll give you some information about that at the end of this talk that goes into way more detail on the 4 factors life cycle model. But for today, I'd like to focus on how the model can support development of better judgment for software professionals. The 4 factors model, which I introduced at my company's Software Executive Summit in fall 2013, is based on what I believe to be the 4 core factors that determine most of the dynamics that happen on software projects. And these 4 factors are size, uncertainty, defects, and human variation. I'm not going to go into a great amount of detail on these today. That'll be the topic of many more talks in the future. But just to give you a very basic idea of what each of the 4 factors means, size would refer to factors like diseconomy of scale, failure rate as a function of size, staff specializations as a function of size, different mix of activities for projects of different size, and so on. And if those concepts are unfamiliar to you, that's because they're actually, each of those is a pretty deep topic and worth actually spending quite a bit of time on individually. Uncertainty refers to topics like in different intellectual phases on a software project, the cone of uncertainty, the idea of how we handle uncertainty and requirements through a feature staircase versus feature buildup, how we approach risk management, how we approach applying effort to gain more certainty, that kind of thing. Again, each of these topics is like a talk in itself. Defects includes topics like the defect cost increase dynamic, the lag between defect insertion and detection, the important idea of the effects of series of defect removal techniques, and so on. And human variation, all kinds of ins and outs there too. So what effect human variation has on software engineering research, what effect it has on selection of methods for use by a particular team, the effect that human variation has on the composition of a team, on team cohesion, and so on. So this is extremely brief, just introduction so that you have some idea of what I mean by the terms size, uncertainty, defects, and human variation. You put these together into what I call the 4 factors model. I think what we end up with is essentially something we can treat as a set of templates against which we can compare what we see on a project versus what we would expect to see, and that supports judgment. And I think if you think about how people use the word judgment or think about judgment in common usage, people will talk about judgment coming from experience. And that's kind of interesting. Judgment comes from experience. Well, what is experience? I think experience is essentially the accumulation of templates of what you expect to see, or you might think of it as accumulation of expectations. And judgment then becomes a process of comparing what you are seeing to what you would expect to see or to what your experience leads you to believe you should see. And that comparison of expectation to actual ends up being a reasonable place to start in terms of judgment. And so what we can do with the 4 factors model is we can actually productize it by doing things like creating, say, checklists for each of the 4 factors. And then we can compare using the checklist what we are seeing to what we would expect to see vis-a-vis each of the 4 factors. And I have several checklists here which you can download copies of the slides later and look at in more detail on your own time, or go back over the presentation later and pause it and read the slides. But for now, I really am just going to skim the surface so you have some idea of what I mean by these. So for size, we would look at things like, is the project estimated close to its actual size? Does the schedule permit completion of a project of the estimated effort? Be another indication. Does the size, basically, does the planned size match the real size? Or does the level of planning, the level of requirements work, the level of defect removal work, and so on match the expected size of the project? Do we have the right kinds of staff? Do we have the right numbers of staff? Do we have the right specializations of staff? All these would be examples of applying a size checklist. Uncertainty, we can kind of go through the same kind of thing. Do the project's estimates and plans account for the kind of uncertainty, i.e. do they account for the idea that software project work is inherently a process of reducing uncertainty, at least when it's done well? Does the project understand where its challenges are going to come from in terms of intellectual phase profiles? Is there uncertainty that's managed well? Is there a plan for addressing uncertainty in requirements work, in design work, in technology, and so on? And so we would go through our project and take a look at how it stacks up in terms of uncertainty. In terms of defects, same basic kind of process. Is the project using practices that will minimize the gap between defect insertion and defect detection? For example, do we have a series of defect removal techniques that are capable of producing the desired level of quality? Do we have the right quantity and kinds of defect removal activities for the kind of uncertainty found on the project? So there's an interplay there between defects and size, and an interplay between defects and uncertainty. And as we get into the 4 factors model, we find there are interplays in every possible combination. We don't really have time to talk about that today, but that is something that I get into in a lot more detail in the lecture series. And finally, human variation. We also have similar kinds of considerations. We want to take a look at how the project is being conceived and executed and throw that against what we would expect to see for a project of this size, for a project of this desired quality level, for a project that has the uncertainty that this project has. So do we have the right kinds of people? Do they have the right skills? Do we have the right numbers of people? Are the people organized in a way that makes sense for the nature of the project? And so on and so on. And of course here we would also be talking about softer factors like what's the motivation level of the people on the project, what kind of staff turnover do we have, what's the geographic distribution of staff on the project, you know, or we have a team that's spread across 12 different sites, or are they all co-located in one site, what's their experience level, and so on and so on. When we put all this together, for purposes of this presentation anyway, I'm going to have a simplified view of this, which is I'm just going to have essentially a red, yellow, green stoplight evaluation of the case studies that we are going to turn to next. So this is really a very simplified view of the model, but I think it's appropriate for kind of at least giving you an introduction to how we might use the 4 factors model to support judgment in software engineering. So let's turn now then to a few case studies so we can actually take a look at what it would be like to apply judgment, particularly judgment based on the 4 factors model, to actual software projects. And as I said earlier in the talk, or as I hinted earlier in the talk, I think a deep understanding of the 4 factors actually supports dramatically better software engineering judgment than we usually see. And I think understanding of the 4 factors also supports better synthesis or creative in the Bloom's taxonomy sense as we take a look at planning and management of software projects as well. And case studies, I think, are a very useful tool because they give us experience recognizing patterns. We can go through them much quicker than we can go through our own experience, and so case studies become actually a really abbreviated way or accelerated way of gaining experience that otherwise might take a very, very long time to gain indeed. So first case study we'll look at is Healthcare.gov, circa 2013. I like this case study just because it's very well known to most people in the U.S. anyway, and it certainly is the highest profile challenged software project in recent times. Basic background on Healthcare.gov is that Congress passed the Affordable Care Act in December 2009. That was signed into law in March 2010. Contracts were awarded for development of Healthcare.gov in 2011. The original project budget was about $100 million, and then coding by the prime contractor, CGI, began in spring 2013 for an October 1st, 2013 go-live date. The cost by the time the system went live was almost $300 million versus that original $100 million budget. And as you probably recall if you're in the U.S., when the system went live, it was plagued by slow performance, downtime, lost data, incomplete functionality, and lots of other problems. And one estimate at the time was that only 1% of people were able to use the site as intended during its initial launch. So that's all kind of the documented history that happened within the first month or so of the release. Now, the newspaper reports that came out at the time were pretty interesting in terms of how the people involved with Healthcare.gov diagnosed the problem. And so here's a report from USA Today. The headline is, "Government did not test the healthcare site as needed." So that would make it seem like this had something to do with testing. And in case that's not clear, the subhead also says that the agency did not test the Health Exchange website as much as it needed to. So it seems like they're pretty on message about this being about testing. The first paragraph, first sentence says, "Not enough tests were performed." The second paragraph, the first sentence says, "The system just wasn't tested enough." So we are seeing very clearly that the reports at the time were that the issue was about testing. That was how the people involved in the project were diagnosing the problems. They were saying the problem was the system wasn't tested. Well, let's take a look at some other details that were published at the time about the project. So here's one comment from USA Today. "We all know we were working under a compressed time frame to launch this on October 1st. Well, compressed time frame, that's interesting. I wrote a whole book about compressed time frame when I published Rapid Development almost 20 years ago. There are all kinds of dynamics that come into play when you're working under a compressed time frame, and if we actually open up the cover and look at Healthcare.gov, many of the phenomenon we see with Healthcare.gov look an awful lot like the phenomenon that we see for projects that are working under compressed time frames. So that's interesting. Another comment, during the House hearing, contractors said CMS decided at the last minute not to allow people to shop for plans before learning what kinds of tax credits they might receive. Decided at the last minute. Does that sound like testing? No, I think that sounds a lot like requirements changes very late in the project. So that's not about testing. Here's another comment. As late as the last week of September, officials were still changing features of the website. And this is just crazy. They were talking about an October release for a $100 million budgeted project, and they're changing features within a month of the go-live date. Again, this is not about testing. This is about uncontrolled requirements changes. Here's another comment. They had just 2 weeks to test the site before all the pieces from several contractors had to work together the day of the launch. I could spend an hour just talking about that one sentence. All the pieces from several contractors had to work together the day of the launch. That implies that they weren't actually integrating and testing as they went, but the plan was to bring everything together in a big bang style of integration, which frankly the industry had decided to move away from sometime in the 1990s. It's quite distressing as a taxpayer to read this report that Healthcare.gov was being created using development approaches that were outmoded by 20 years or more. And then this basically other comment, it was the agency's responsibility to make sure all the parts work together. To me, this falls directly from the idea of working under a compressed time frame. Basically because there was so little time to do the work, none of the contractors wanted to step up to making sure all the parts work together. That responsibility by default went back to the agency. The agency wasn't capable of performing that work, and so of course it didn't actually happen. And finally, this comment is the one that really floors me. The technology is there to make it work. It just requires foresight. Wow, it just requires foresight. In other words, it just requires planning. And I think we can see just from reading the paper that there were all kinds of issues involved in Healthcare.gov, really very little that had anything to do with software testing. So how would I evaluate this according to the 4 factors model? Well, I think if we look at the size, we had a short schedule that was basically mismatched to the size of the project, a huge budget, huge staff ramp up. I think we get a big red circle on size, so lots of risk there. Uncertainty, we have numerous immovable requirements or laws, so not much uncertainty there, but we have massive requirements changes and significant unprecedentedness, meaning it's a newish system. I give that a big red circle as well. Defects, approach to QA was not matched to the size of the project or nature of uncertainty. We can see that just from reading the newspaper. I think we give a big red circle there too. Now human variation, you know what? This is where judgment comes into play. It doesn't matter. We know enough from the fact that size, uncertainty, and defects all get big red stoplights that this project is going to be significantly challenged or fail just on those 3 attributes. Human variation could knock the ball out of the park, and it wouldn't matter. The project would still be extraordinarily challenged. Now, it's an interesting footnote to this whole episode is that in July 2014, the Government Accounting Office, or GAO, came out with its report on the problems with Healthcare.gov, and they substantially matched my analysis from reading the newspaper back in November of 2013. The GAO report said that Healthcare.gov suffered from a rush schedule, changing requirements, lax oversight of contractors, and lack of effective planning and oversight practices. And my point, and the reason I'm giving this presentation, is that I think that anyone who understands the 4 factors model could actually go through the same kind of thought process that I went through in looking at Healthcare.gov and would come to the same conclusions. I'm not saying that what I'm doing requires any special skills, but it does require an understanding of software project dynamics that goes beyond what we see from many people in the software industry today. And so that's really the purpose in presenting the 4 factors model. Let's take a look at another project. Strangely enough, this is another healthcare system, but this is the state of Oregon's healthcare system called Cover Oregon. And the background on Cover Oregon is that in 2011, Oregon decided to develop its own state-level health exchange rather than using the federal government's Healthcare.gov. They began work in 2012 for the same October 1st, 2013 go-live date as Healthcare.gov. They contracted with Oracle to develop the exchange, and they received $300 million in federal grant money to develop the site. Now, I leave that as an exercise to the reader to figure out how anybody thought the federal system could be developed for $100 million, whereas Oregon needed $300 million, but that will be something you can figure out on your own. And as of December 2013, Oregon's exchange was still not working. Oregon reassigned 500 staff to process paper applications, and by April of 2014, the exchange was still not working. The state shut down Cover Oregon, and Oregon adopted Healthcare.gov beginning in 2015, so earlier this year. Now, interesting thing about this is we see bad judgment here across the board. The bad judgment is not just limited to software. KATU reported that Cover Oregon had spent 2/3 of its money, so about $200 million, and that to date they had signed up more than 63,000 people, which generates a per member per month fee of $9.38. Now, if we apply a little bit of math to this, we can see that $200 million divided by 63,000 people means it costs them over $3,000 per person to sign them up. That's just access to the exchange. That doesn't include the health care. That's just to sign them up. They're getting $9.38 per month per enrollee. So if you take that $3,000 and you divide it by $9.38 per month, you'll see it'll take 28 years to pay back the investment in the system, except for the fact that those people weren't signed up using the system. They were signed up on paper by the 500 people who got diverted. The system never actually signed up anyone. So the reported problems with Cover Oregon were just massive. And this is from a report that was done by an independent assessor. They found the code quality is subpar. There was no impact analysis prior to coding, no peer reviews, no detail on the software check-in, check-out, or merge processes, bad build process, no skilled management, bad status reporting, poor design, even worse code. They broke every single development best practice that Oracle themselves defined, and they lacked the skills, knowledge, or ability to be successful. I can't really think of how you could possibly have a more damning report. So if we apply the 4 factors model to Cover Oregon, here's what we find. Size, we had a huge budget, huge staff ramp up, and this is critical. No aspect of development was matched to the size of the project. So we get not just a red circle here, we get a big red circle. Defects, we had 0 meaningful QA practices and evidence. Again, big red circle. Human variation, massively underskilled for a project of this size, and so another big red circle. Uncertainty, you know, this is another case where we can apply judgment. It doesn't matter. If we do so poorly in size, defects, and human variation, we could have the most certain project in the world, and it would still go very, very poorly. Now, I think one of the things that's interesting about this is these aren't just little red circles. These are huge red circles. They're blatant mistakes, and there is absolutely nothing subtle about what went wrong with this project. I'm sure some people listening to this talk would say, wow, I mean, how could anything be allowed to go so catastrophically wrong? They did so many things badly. And the thing that's interesting about that is this project actually had a higher level of oversight than your typical commercial project. This was a project run by the state government. It had oversight by the state agency, by elected officials within the state. And so, for sake of argument, you could actually say this project should have actually been monitored more closely and had a better chance of success than average, but in fact, it went bad for some very, very blatant reasons. And this goes back to my point. The issues here are not about analysis or fine points in the details. The issues here are all about large grain decisions that went wrong. The very first decision in this project of spending $300 million to do something of a relatively modest scope was probably the big decision that went wrong in the first place. And there are lots of other big decisions, any of which would have caused the project to fail. The poor staffing, poor management, poor sizing, everything. And the joke here is the 1980s are calling. They want their project back. I've been doing this for a long time now. I've been doing this for 30 years. And it seems like this case study is so blatantly bad that it's almost contrived to make a point, but it's not. And you would think we would have learned these lessons decades ago, but this project was still ongoing last year. I think the problems on this project are obvious, but you know, maybe I've just been doing this too long and I can't see it anymore. There's a great book called Made to Stick that describes something they call the curse of knowledge, which basically says if you're too familiar with something, you lose your ability to see how other people are unfamiliar with it, and that makes it difficult to explain it. And so the more time goes by and the more time I spend in the field, the more difficulty I personally have knowing what is obvious to other people and what is not. The problems in this project seem obvious to me, and yet this project was allowed to go wrong by intelligent people. These were not stupid people. They were intelligent people. They had multiple levels of oversight, and it went wrong to the tune of $200 million. So something here is not obvious to other people. The commonalities that this has with other case studies are that we're not talking about an absence of analysis or subtle miscalculations. We're talking about gross errors in judgment. And I think we ask the wrong question sometimes when we say, what went wrong with this project? The right question is, why did anyone ever think this project would be successful? I have a belief that it's a more constructive posture to look at projects, and instead of assuming they'll go well, your starting position is to assume that the project is going to fail. In other words, you're guilty until proven innocent. Prove to me that the project is actually going to work. Prove to me why it won't fail. I think that's a much more constructive planning posture than the opposite. Let's turn now to a little bit more subtle example, the Chrysler C3 project, which was the original extreme programming project. And this is certainly not the failure that we've seen in the first two examples. So the background on the Chrysler C3 project is that Chrysler wanted to replace several disparate legacy COBOL payroll systems with one system. They commissioned various groups to work on it. They didn't make much progress from 1993 to 95. In 96, Kent Beck was hired to build the system, and he in turn brought in Ron Jeffries. So these are two rock star programmers working on this project. Kent and Ron implemented pair programming, continuous integration, on-site customer, unit testing, refactoring, you ain't going to need it, all the practices that became extreme programming. Their initial release was 2 months late on a 12-month schedule, but the team considered that to be basically on time, given the track record of multiple years of nothing getting done before them. Once they did that initial release, the progress for the next few years, however, was mixed and characterized by just one more requirement syndrome, meaning they always needed one more requirement and couldn't quite bring the thing into completion. The further releases were finally halted when Daimler acquired Chrysler back in 2000. So how would we apply the four factors model to the Chrysler C3 project? Well, I think the size is pretty small. This is a small project. Their planned scope was pretty close to the real scope. Their approaches made sense for a project of that size. They were scaled appropriately for the sizes, so I'd give them a green light in terms of size. In terms of uncertainty, on the plus side, payroll is a well understood area, so that would give them a green light. On the other hand, they have lots and lots of legacy systems, and there can be tons of undocumented, subtle requirements in those legacy systems. So given that we might have conflicting requirements and so on, I give them a yellow on uncertainty. The approach to defects, I think the practices they used were quite reasonable for removing defects for a project of that size, and I don't think it's a terribly high defect potential project in the first place. It's basically replacing existing systems with a new system, so they at least have de facto as-built existing systems to look at. I don't see super high defect potential in this project. And then the final attribute here, human variation. We had Kent Beck on the project. We had Ron Jeffries. We have two phenomenally capable individuals on the project, and it's not that large a project. Human variation basically is such a positive on this project, I think it kind of drowns out every other factor. You take these two guys on a relatively small project, they're going to find some way to make that project work. So based on the four factors model, what surprises me about the Chrysler C3 project? And the answer basically is nothing. Nothing surprises me about this project. This project actually worked out exactly like I would expect with these kinds of project attributes and this quality of staff on the project. I don't think there was any secret extreme programming secret sauce that's significant on this project because the human variation factor just drowns out everything else. If I apply the question I asked a few minutes ago of why did anyone ever think this project would be successful, I think there are lots of reasons to think this project will be successful. They have highly skilled, capable people using reasonable practices, and the project succeeds. And so to me, the lesson of Chrysler C3 is not about extreme programming. It's if you pay attention to the needs of the project and plan and execute accordingly, the project will be successful. And that, in fact, I think, is what we saw in that project. The final case study I'd like to take a look at today is the Cheyenne Mountain ATAMS project. In the lecture series, I'm going through many more case studies, but for this today's talk, this is what we have time for. The context for the ATAMS project is that the United States Air Force had a project called Cheyenne Mountain Upgrade that was originally scheduled to last 6 years and cost just under $1 billion. 13 years later, the Government Accounting Office estimated that CMU was $1 billion over budget and 11 years behind schedule, and the new systems that had been completed were not usable. And so against this backdrop, the CMU managers commissioned Cayman Sciences to conduct the project called the ATAMS project. And their goal was to replace displays on 20 monitors with displays on just 2 and to improve response time. Their project constraints were a schedule of 1 year and a budget of $2 million. The Cayman Sciences company appointed an experienced project manager. They took an 11-person impact development team and applied them to the project. The team extensively prototyped user experience. When they did that, their user demands turned what had been a 2-message 4-display system into a 57-message 35-display system, but this was all discovered during prototyping. That is very early, before any actual software had been written. The team had the discipline to attack the riskiest elements first. They always asked, what is the riskiest thing, what is the thing that's the hardest, and they worked on those things first. They did disciplined design reviews, and they caught more than 200 major defects and 500 minor defects at design time at a cost of slightly less than 1 staff hour per defect found. They performed root cause analysis for each defect they found, and they asked, how could we have prevented that defect from occurring? They performed technical peer reviews throughout the project. They had active management to ensure that peer reviews were performed ongoing in a timely way. The team adopted a standard of perfecting each component, that is, removing all the defects before moving on to the next component. And they published their project status in a graphic format so that anyone could see where anyone was at any point in the project just by looking at this graphical information. And the project management in turn used that status information to seek out project risks and actively address them. The result was that ATAMS was delivered 1 month early on a 12-month schedule, and only 2 defects were found within the first 16 months of operation. So how does this score according to the 4 factors model? Well, in terms of size, we've still got a fairly small project. A 1-year schedule, 11 people. I think this gets a green light in terms of size. In terms of uncertainty, this is really the area of this project that makes me nervous. We have significant requirements changes, but we have practices that actively attack the uncertainty. The prototyping uncovered those areas of uncertainty early. The project actively attacked quality risks, project planning risks, and requirements risks. So while it's yellow, the active work on the project kept that yellow from turning red, and that's a positive. On the defect front, I think this is just a clear success story. They had early defect detection of requirements through prototyping. They had thorough reviews. They had an ongoing emphasis on perfecting each component and maintaining high quality and high discipline. And human variation, we had skilled management combined with an intact team. So overall, I think it's not that mysterious why this project worked well. It's mostly green, does well on size defects and human variation, and well enough in those areas to overcome the risk in the uncertainty area. So if we compare to the commonalities from the other projects we've seen, what we saw in the first couple projects is people on the project seem unable to identify even basic dynamics on their own projects, even in hindsight. We see the exact opposite here. There is an awareness of risk and explicit steps taken to address the risk, and we end up with a very successful project. If we ask the question asked, why did anyone ever think this project would be successful? I think it's pretty clear. There are lots of reasons to think that this project would be successful. And finally, if we compare to commonalities from the other projects we've seen, the problems are not subtleties but gross errors in judgment. No, there were no gross errors in judgment on this project. And what's interesting, I think, is that the causes of success on this project seem as conspicuous as the causes of failure did on the other projects. All right, well, now having presented Bloom's taxonomy, talked about judgment, having looked at the 4 factors model and applied that to a few case studies, what could we conclude? Well, most of what I've described today seems obvious to me, but then again, I've been doing this for a very long time. I think one common theme in the failed projects is that basic project dynamics, we're not talking about subtle project dynamics, we're talking about basic project dynamics, were not obvious to the people involved in these projects, even highly intelligent people, and often even in hindsight. If we were talking about dummies, I'd be giving a different talk, but the fact of the matter is that these are smart people who are still making these mistakes. And the question is, how can people who are so smart make such bad decisions? And I go back to my original point, which is that software professionals tend to be very strong in analysis, so the deficiency in analysis is not the problem. What is the problem is deficiency in judgment. And we find that deficiency in judgment, even gross errors in judgment, are common in software. And for that reason, I believe that a focus on developing judgment in software professionals is important, perhaps more important in software than in professions that do not select so strongly in the first place for analysis skills as software does. And for more on this topic, as I mentioned at the beginning of the talk, I have a lecture series about the 4 factors lifecycle model that we will be releasing by June 1st. You can see the URL on your slide here. It's cxlearn.com, pretty simple, cxlearn.com. If you go there today, you can find a place to sign up to be notified when those lectures become available. But we are targeting a release date of right around June 1st for those, and then those should be released for quite a few months after that on about a bi-weekly basis. So at this point, I will turn the microphone back over to a moderator and see if we have any questions.
Thanks, Steve. And we do indeed have a few questions come in. And just a reminder to everybody, if you do have some questions, we'll try and get to as many as we can in the few minutes we have left. So please feel free to enter them now. I'll save you from questions about the congressional hearings around Healthcare.gov, Steve.
Thank you.
Yeah. So let's just start with the checklist that we hammered about early on in the presentation. There's some concern expressed by some attendees that the checklists themselves may be a little bit restricting in terms of how they help people go through the analysis and judgment piece as opposed to just free thinking.
Andy, would you mind repeating that question?
Sure. So there's a few people expressed some concerns that the checklist that you talked about early on as a way to think through the 4 factors may be more limiting to thinking than if we allow people to just sort of talk through the problems or think about what the concerns might be rather than sort of trying to put them into the framework of a checklist.
Yeah. So that's an interesting concern. I guess my response to that would be, if we take a look at the more challenged case studies and we say, what if early in those projects somebody had gone through those checklists? Would those case studies ever have happened? Would it have been possible to have the disaster of Healthcare.gov or the disaster of Cover Oregon if people had gone through those checklists and there had been some visibility around those and oversight and so on? And I think the answer is no. It would have been impossible. You couldn't go through those checklists and say, yep, everything's fine on these projects, because everything wouldn't have been fine. There would have been glaring errors. And then I think conversely, you say, well, what if we take the successful projects and we go through the checklist on those? Well, you know, the point of the checklist is not to answer an affirmative yes on every single item. The point of the checklist is to say, did you at least think about this? And I think if you went through the Chrysler C3 project, you'd find some areas where you'd say, huh, yeah, this is actually potentially a problem. And likewise, on the ATAMS project, you'd find some areas where you'd say, yeah, this is potentially a problem. But in essence, going through this kind of a checklist is exactly what they did on the ATAMS project. And so that put them in a position to actually be proactive in addressing the potentially problematic areas of their project. And as a result, the project ended up being very successful. So I don't really see the risk. I think in our industry today, the risk is much more on the side of people using informal ad hoc practices or no practices at all and ending up with really unsuccessful projects. We've had some good advances over the last 15 years in software development, and Scrum in particular I think has been a huge advance in software development. But we still struggle with larger projects, and for the amount of money that we spend on software projects, the level of planning and risk management in software still pales in comparison to what we would see in almost any other human endeavor where we spend that kind of money. So, I'm not talking about spending several months going through some huge checklist and spending $100 million going through the checklist, but I am talking about doing at least a little bit of planning and diligence before we actually spend millions, or in some cases hundreds of millions of dollars.
Excellent, thank you. A couple of related questions that came in from people around the timing of applying the four factors model. One person was asking about whether or not we could apply this during a project. Somebody else asked about whether or not we could do this in a predictive manner at the start of a new project, whether or not that's been tried, and if not, how we might go about doing it.
Yeah, the four factors model is much more rich and elaborate and broadly applicable than I've been able to present in this one talk. I think that if somebody really understands the four factors, which is the point of the lecture series I mentioned, that whether they go through a scripted approach using it like the checklist that I suggested, or whether they just internalize that way of looking at software projects, I think they will be thinking about projects from the four factors point of view all the time. And that applies end to end. So project planning as the project is underway, and doing post-project retrospectives. It's just a way of looking at a project. And the checklist that I presented is by no means the be-all and end-all result of the model. It's just the easiest way to communicate kind of the gist of the model in a very short talk for one purpose, that is looking at case studies today.
Excellent. I'll try and get one more quick question in the last couple of minutes, and that's around things like CMMI. There's a comment or a question that came in around some of the different software development models, and CMMI was used as an example that we sometimes see in software development, and how that might align with some of the upper levels of this model.
Yeah, I'm not sure there's any direct correspondence. CMMI, you know, if you'd been asking this question 15 years ago and we were talking about the software CMM with CMMI on the horizon, I think there was a lot of currency of software CMM for a few years. CMMI, I think, basically really narrowed down the applicability of CMM, so we just don't run into it that often anymore. I know that there are still companies, especially like large government contract companies, that use it, which of course was the original purpose of the CMM back in the late 80s, early 90s. But yeah, I think I see them as kind of different ways of looking at similar issues, but I don't think there's any direct correspondence.
Excellent. I did promise people that I would give them information on the PDUs, so I will get to that, but I just wanted to share one comment with you as a final thought, and that is, and I'll just read it, this is one of the best in capital letters, webinars I have ever attended. Thank you to the presenter. So don't get too excited there, Steve. It was only one of the best, not the best.
Yeah, was that commenter's name Steve M?
No. Oddly enough, that looks like a genuine comment.
Outstanding. Thank you.
So thank you, Steve. As always, it was a wonderful presentation. Just for everybody's sake, the PDU information for this, this is eligible for a Category C PDU. That is a PDU that you need to claim yourself through the PMI Continuing Education section of the website. So all the information will be included in the email that is sent out within 24 hours of this, which will also include the link to the slides and the link to the recording. But please remember that this is a self-declared PDU category. It's not one that's reported automatically for you. So, Steve, thank you so much. Wonderful presentation. Thank you, everybody, for attending. And please join us again for the next webinar very soon.